So we've looked at the mechanics of one person standing in line, but obviously that's not really the model that we're interested in. Let's see what happens and how other people join the line. Okay, so that's the next piece that we're going to look at, and then we're going to put everything together. So we're going to assume kind of a similar idea. We're going to assume that every delta t units of time, there's a lambda times delta t probability that someone joins the line, okay, that they arrive in the line. So probability every delta t units of time, there's a lambda delta t probability someone joins the line. Okay? So, okay, great. So what we're going to do is we're going to build a Markov chain like this. And if you think about this Markov chain, what's going to be your states here really are the number of people that are in line, right? If you think about this for a second, what is this probability? This is the probability that the number of people in line increases by 1. Okay? And so we're going to have a state where there are 0 people in line, a state where there's 1 person in line. The probability we go from 0 to 1 is lambda delta t in any particular delta t units of time. The probability we stay in 0 is 1 minus lambda delta t. Okay? Well, that's simple enough, right? But of course, from 1, what happens leaving this one? Well, there's a lambda delta t, lambda times delta t probability that you go from 1 to 2, a 1 minus lambda delta t probability that you stay in 1. Same way to 3 people being in line. Lambda delta t, 1 minus lambda delta t. Now, unless there's some finite limit on the number of people that can show up in line, which there is, right? You know, there are 10 billion people on the planet, or 8 billion people on the planet, whatever. So that is a finite limit. But this can keep going up and up and up, right? There's going to be a 4 and a 5, and so on and so forth. So this is an example of an infinite Markov chain, okay? So if we really want to think about the theoretical model, it's actually infinitely long. It's got a state for every number 0, 1, 2, 3, 4, 5, all the way up to infinity, okay? And that seems a little intimidating, but it works the same way, okay? Now the solution is a little bit strange. We're not gonna necessarily talk about it, but let me show you the idea of what's going on. From this Markov chain, we can create a matrix. And what we're going to do is we're going to create functions p0 of t. So p0 of t is the probability, let me say pi and I of t in general, is the probability we're in state I. Right, which is to say the probability that there are I people in line. Okay, so p sub 0 would be the probability that there are 0 people in line. P sub 1 would be the probability that there is 1 person in line. Make that English. P sub 2, probability 2 people in line, so on and so forth. Okay? And so what you end up getting from your Markov chain is a matrix that looks like this. So if you want p sub 0 of t plus delta t, you're going to take 1 minus lambda delta t in the p sub 0 piece, 0 everywhere else, and take that times p sub 0 of t. Okay? So 1 minus lambda delta t times p sub 0. P sub 1 of t plus delta t is going to be lambda delta t times p sub 0, and then 1 minus lambda delta t times p sub 1 of t, and then zeros everywhere else. okay? Because you've got lambda delta t probability that they're coming from 0 to 1, 1 minus lambda delta t probability that they're staying in state 1 if they're already there, okay? Next line will be 0, lambda delta t, 1 minus lambda delta t, 0, and so on and so forth. Right, times p sub 2, p sub 3. And this keeps going all the way to infinity. So these are all infinite dimensional matrices. You may have heard something about some of these in linear algebra, but it's very intimidating, right? But don't let it be. So it's very simple. What we end up getting are kind of very simple differential equations. If you follow the same kind of process that you did before, so p sub 0 of t plus delta t is 1 minus lambda delta t times p sub 0 of t. So that looks very familiar. That's exactly what was going on with a lambda instead of a mu in our previous situation. We can solve it the same way, move terms over, take the limit as delta t goes to 0, and we'll get that this has an exponential solution. P sub 1 of t plus delta t, a little bit more complicated. It's lambda delta t times p sub 0 of t plus 1 minus lambda delta t p sub 1 of t. P sub 2 is going to look very similar, but with p sub 1 here and p sub 2 here. P sub 2 of t plus delta t is lambda delta t p sub 1 of t plus 1 minus lambda delta t p sub 2 of t. And so you can keep building up these equations, and you can solve them into differential equations just like we did before. We're not going to do that, right? Don't worry about it because these are a little bit more complicated. But what you end up getting is that p sub 0 of t is exponential. It's going to be e to the negative lambda t. And then p sub n of t for all the others, for any n greater than 0, is going to be e to the negative lambda t times lambda t to the n over n factorial. Okay, and this is what's called a homogeneous Poisson distribution. And so this gives you the probability that there are the probability that you are in a particular state, right? That you've got n people in line is going to be this probability. Okay? So at a particular time t, what's the probability that there are n people in line? So if you look at it, the probability that there are 0 people in line decays exponentially. We expect somebody to show up. Okay? The probability that there are n people in line also decays exponentially, but bumped up a little bit, right? Because it's going to be later on that there are n people in line. Okay? So this gives us equations that fit this. What we're going to do next is we're going to build a full model of a queue where both people arrive, like they are here, and they leave. I'm sorry, this is people arriving. Then we're going to implement our single person leaving the queue model when they're being served, and we're going to see how we can build the whole thing up.